everyone, welcome back to the latest lecture session. As is the norm, a quick recap of what we have been up to. In the last couple of sessions, we've been looking at or we've been discussing settling, different types of settling in the context of primary treatment, right? Why were we trying to settle particles and such? Because we have these bigger particles which can be removed with the assistance of gravity, so that we decrease the load on the biological process where we need to provide oxygen and which thus requires money or resources, let's say, right? So in that context, we looked at different types of settling. Type 1, discrete, right? Each particle does not interfere with the other. In this context, obviously, we looked at gravity. So we looked at three forces: gravity, pulling it down; buoyancy, yes, due to the relevant fluid there; and then the friction or the drag force, let's say. When all these three, negate each other, right, we have the particle reaching its terminal velocity or the settling velocity, right? And we looked at how, people came up with the Stokes law, and that was applicable when Reynolds number was less than 1, or even is applicable when it's less than 100, but it's applicable in laminar flow and when we have spheres, let's say, right, and when we are discussing spheres. And in that context, we moved on, we discussed some aspects, and then we moved on to looking at type 2 settling, wherein, due to difference in velocities and the fluid, or, a bigger particle and a smaller particle having different velocities of settling and then coming together, right, we were looking at flocks being formed, and then flocculation or flocculant settling, which was type 2. And then we looked at how to, understand the system and try to design it. And we looked at, some data and looked at one example. In that context, let's clear up some aspects or discuss them. So here we have discrete settling of particles, right, where, let's say, gravity minus buoyancy equal to the drag force, right? So the particle has reached its terminal settling velocity. So what do we see now? If this is the settling column, right, and we see that with depth it decreases. Obviously, this line is going to be a straight line because now the velocity is constant and it's discrete settling now, right? That's something that's not a no-brainer. Obviously, here we are considering that all the particles are more or less are of the same size, let's say, right? So that's why we have entirely clear liquid at the top and particles being concentrated at the bottom out here. Yes. And what do we have here? So general inferences, which we discussed earlier, but I want to discuss one aspect which we will look at later, let's see, right? This is the aspect. So if I want to calculate the concentration in the mixture, which we are referring to as mixed, calculate the concentration of the relevant suspended solids in the mixture. So I need to understand that there are two zones, right? Yes. So I need to look at weighted average, as in for this zone I need to average it or weight it by the concentration of the TSS in this zone, and for this zone, right, I need to weight it by the concentration of the TSS in this zone. Whatever has settled down right at the bottom, we are assuming that that's not present, let's say. So for this particular zone, let's say, what do we have? We know, let's say, or we assume that the concentration is C naught, let's say, okay, which is the, I guess, more or less the initial concentration, okay. So what do we have? C naught into Z minus H, right? Z is this, and we are subtracting H, right? So we are looking at Z minus H by Z, right, into C naught. That gives us the concentration in this particular layer, and we are looking at weightage, obviously. And in the above layer, H by Z, let's say, there is no, suspended solids, that's why we have 0. So C mixture, it's equal to C naught into Z minus H by Z, let's say, right? The concentration is uniform here, that's what we always have. So let's move on. We will look at this later again, but please keep this in mind, as in we are weighting it by the concentration in that zone, right, or we are considering the concentration in that zone and also weightages, right. We are looking at the height of that particular zone, let's say, right. So that's something to keep in mind. Unlike the previous case, if we have different particles with different terminal velocities. So here we have an example. Again, this is from Professor Markham Benjamin, right, who wrote the book Water Chemistry. He is pretty famous for that. So we have different particles with different sizes, and thus let's say terminal velocities, let's say, right, settling velocities, different settling velocities, and the concentration of these settling velocities, I mean the compounds with these settling velocities is given out here. And then we have, let's say, data of how much distance they have fallen after different times, right. So obviously if a particular particle has a greater settling velocity, that is going to travel a greater distance. If it has a lesser what do we say settling velocity, it is going to travel a lesser distance. Again, here we are still assuming that it is discrete what do we say settling. So if this is the initial picture, right, and these thickness more or less indicate the concentration, if I am not wrong, right. So after 10 minutes, the one with the relatively what do we say slow settling velocity or less settling velocity only settles a bit, and the one with the greatest or highest settling velocity settles a lot. And I guess here we are talking about what do we say 50 centimeters. So that was already reached for this particular particle, and so progressively the other particles too keep settling down. So this is more realistic because in wastewater you don't have particles of just one size, but particles of different sizes. Obviously here we are assuming different what do we say or having some assumptions, but we are not going to go into that now, let's say. So what is the profile looking like right now? It's the total concentration at any depth is the sum of the concentration of the particles at that depth, pardon me. So again, what is the profile looking like, right? You see this profile, yes. So these are the assumptions, or these are some of the inferences out here. But again, we are not going to look at that in detail. But if you look at these, what do we say, inferences or such, we see that it's typically not practical, or it does not really happen in that way. So a more realistic one would be, when suspensions contain particles of virtually all velocities, so that rather than this step kind of distribution, we see this step kind of distribution, we have a continuous, what do we say, distribution like this, let's see, right. So that's one aspect, fine. But again, all these aspects we were discussing were about type 1, discrete, but we know that that's again rarely the case. Mostly we come across type 2. Here we have a good figure, effect of particle agglomeration, or let's say flocculation on settling. So particle A, this is the profile, particle B, this is the profile, but because they came together due to, let's say, either differential or different settling velocities, or due to different fluid velocities there, they came together, and now you see that the floc settles faster, let's say, right. Again, type 2 settling, where we have flocculent settling. So this is what we usually encounter, and we looked at one example, but let's just look at it in some detail, let's see, right. I believe I rushed it the last time, so I want to discuss this in detail. So we got data, we plot the percentages, and then from those percentage removals, we can get the, what is it now, what are they calling that, isopleths, I guess, which are more or less nothing but constant removals, let's see. So this can be for 30, okay, for 40%, 50%, 60, 70, 80. This you will get based on interpolating the data which you measure at different depths. This is the actual data, and you are interpolating here, right. So how does this help me, let's see. So let's say I am going to choose a particular time and depth. So at this particular depth, I know the time here, right. That's how we have, this is x-axis time. So at this particular depth, what is it that we know here, okay. So removal at the bottom of the column, here it's 42, I guess, maybe I am looking at this, is it, okay, and it's 100% at the top, let's see. So maybe this has to be corrected, it's not 42, let's say, right. So that's what we have, but I know that it's 50, or at the relevant point of intersection here at the bottom, and let's say 100% about at the top. But here you see that there are still particles with varying, what do we say, levels of removal, or at different depths we have different levels of removal, let's say. So how do I get the total concentration here? So similar to what we did in discrete settling, we are going to look at giving the weights, as in terms of depth, we know the depth, and here the average removal will be 60 plus 50 by 2, 55%. And here this is what we have, and for this zone or height we will say it's 70 plus 60 by 2. So that's what we have, 55%, 65, 75, 90% corresponding to this height, let's say, in the relevant column or the sedimentation tank, right. And from that we got that relevant removal. If you remember, the total removal was nothing but removal at this point, right, or total removal at this point plus what now, this particular what do we say, height, where we look at the midpoint, I guess, and then we looked at the average of these two particular values, 60 plus 50 by, what is it now, 60 plus 50 by 2, and then into this h, if I say, or delta Z4 by the total here, total depth, let's say, is h, let's say. So in this way we looked at it earlier. So in the same case, I guess you can what do we say, analyze it for any system, right. And we also looked at effect of depth, and we know that, let's say, okay, let's understand this figure. We calculated the overflow velocity such that the particle, if it just comes out at the top and has this settling velocity equal to this overflow velocity, it will just be removed, let's say, right. So this settling velocity is obviously in the downward direction, but the water is taking it in this direction. So the net will be in this direction, and that's what we have out here. So this velocity is due to the relevant fluid flow. This is due to the settling of the particle. So if a particle has settling velocity equal to V naught, it will just be removed. That's what if we see. But if the particle coming in at the same location has a settling velocity less than V naught, obviously it's not going to be removed. That's what you see out here, right. So that's something we already discussed. And then we looked at the depth. For example, if I decrease the depth, right, what's going to happen here? The overflow velocity, if you remember, is how did we calculate that? I think we calculate that by looking at Q by the top what do we say, area, let's say, or surface area, pardon me, right. And here we have Q by length into width, and we don't have height out here, right. So mathematically we can see that height does not affect your overflow rate and thus your removal efficiency. Let's just try to understand it here. If I decrease the height and the flow rate is still the same, so this velocity of the fluid will now be twice. You can look at the relevant algebra, that's pretty simple, right. And now the height is lesser, let's see, right. And again you will see that it's still the same though, right, V naught and still V. So the lesser height, lesser time available, let's see, right. So that's what you will have. So even though we have less height, you will now have lesser time for the particle to spend in this reactor and settle down. Again, the whole point comes down to whether the settling velocity is greater than or less than what is this, V naught. If it was twice though, instead of h it was 2h, it might seem like there is more time though, right. That's true, but then the particle also has to what do we say, settle down for twice the distance, let's say, right, or twice the height. So both ways you see that height does not affect your removal efficiency. Only way is to increase that surface area, which can be done by putting in a tray here, right. So in effect you are decreasing the surface what do we say, or increasing the surface area, and thus in effect decreasing the V naught or effective V naught here, let's see. V naught effective will be the previous V naught by 2, because here I am providing a tray here. So now obviously you will have increased removal efficiency for the same volume, but obviously here the case is that we have an intermediate tray. So these were the aspects that we looked at. So let's look at some of the other aspects, okay. So here we have, what do we say, on the y axis the particle concentration, and here different types of settling were mentioned. Discrete settling, when the particles do not influence or interact with the other particles, and then type 2 or flocculation settling, when obviously particles interact and form flocks, let's see. The next one will be hindered or zone settling. I guess we have better figures here, but let's just try to briefly look at it. So what happens is, after certain, what do we say, level of settling, in actuality what do you see? You see particles coming together, right. And now water is, I would not say trapped, but it has to, or it does not have a clear path to go around. For example, earlier water could go around like this or this now, but now you have something like this and water finds it difficult to go out. Only in these interstices between the particles the water will go out. And also because the particles are so close to each other, they also repel each other, right? And in effect you will have what we say decreased settling velocities beneath these particles, right? So that's hindered or zone. Why do we say zone? Because more or less you see that all these particles are entrapped out here, and as these particles settle down, you clearly see a zone above and below. Above relatively clear, below where you have the suspended matter. So that's what you see out here. And compression settling, here it's not as if particles settle down, but let's say because of, if I may use this layman's term, the weight of the what do we say overlying particles, the water in these pores will be squeezed out, right? So then you see more or less compaction or particles compacting, and that we are calling as compression settling, let's say, right? So water displaced from the pores as particles settle and compress the layers beneath it. So discrete, flocculent, hindered settling and compression settling. Let's look at some figures. So rectangular tank, if narrow rectangular tanks anyway, as you can see here, this is the plan top view and this is the side view, let's say, right? Again, narrow rectangular sedimentation tanks are typically much better with respect to removal efficiency, let's say, right? But the issue here is that if you have long, narrow, what do we say, tanks, the area beside it, you can't really use it, right? So it's typically uneconomical for the plant or with respect to the construction efficiency, let's say, even though the removal efficiency might be high. So that's one thing to keep in mind. I believe we have figures for this, for these chains and such. We will look at that. Okay, let's just look at it. So influent out here. So sludge hoppers, that's fine. I guess you see the sludge hoppers from here too. We will not look at that. So again, the water is flowing in this direction and particles that are settled out will be removed by the scraper board. So you will have, okay, I have a better figure later, we will look at that. So that will scrape the sludge and bring that out here. Let's say, okay, you have this, you can see that from the side view. So what's going to happen? These chains moving in this direction, they will scrape the sludge at the bottom, bring it down here, right? So that's what you see. And maintaining these kinds of scrapers is always an issue. So people typically, what do we say, go for this rotating or circular types of scrapers, let's say. Please note that here we still have a rectangular, what do we say, sedimentation basin. What's happening here? We have water coming in, we have baffles out here, right, to distribute the flow, bring down the velocity, right? And then you have, what do we say, a rectangular, what do we say, sedimentation tank, right? But here we do not have scrapers like the earlier case, but we have, what do we say, circular scraper, if I may say so, right? Flocculator and square sedimentation tank for water clarification. And one issue here is that obviously you see you have dead zones out here, so removal of the sludge or particles that have settled out here is an issue, and looks like due to the wear length along this particular edges and such, you can have radial flow or non-uniform flow affecting your removal efficiency. So that's one aspect to consider. Again, side view, as you can see, water coming in, you have baffles here, again mixing to provide flocculation, and then it comes in, right? And then it settles down as it goes through, and here you have these what is it, rake arms, circular rake arms that get the job done with respect to scraping the sludge. But the most widely used ones are going to be these circular sedimentation tanks, where the water comes in from the bottom, and here you have flocculation, right, and then it flows radially. With respect to efficient usage of area within the tank for sedimentation, this is not as good a design as the relevant rectangular tanks or such. But why is it that people go for it? Because they are cheap, maintenance is easier, right? And even, I mean, when I say cheap, the capital costs are pretty less, maintenance is always better. So that's why people typically go a lot for these particular, these kinds of circular sedimentation tanks, right? So that's something to keep in mind. Let's move forth. So when we are designing, primary sedimentation tanks, obviously we need to look at some variables, but the primary variables are obviously the volume of your tank, but that obviously needs to take into account the average flow and also the peak flow. And one reason why we have, let's say, sedimentation tanks of depth 3 meters or so, even though theoretically the depth can be much lesser, is that, let's say I design it for average flow and have a depth of, let's say, 30 centimeters or so, let's see, okay. And then you have the peak flow coming in, and then everything is going to scout up, and you are going to have what we say turbulence in the system and everything being scout up. So obviously you want to prefer or see to it that you can tackle these peak flows, right, and you want to avoid turbulence in your primary sedimentation tank, and also you want to promote flock formation, right. So you always obviously want to, or that's the reason why people go for sedimentation tank depths of around 3 meters or so, even though the design from point of view of just sedimentation, let's say, or the Stokes velocity will tell you otherwise, let's say. And what else? I also need to look at the depth, as I mentioned, typically 3 meters. And once I can get the volume, and depending on the flow rate, I will have the detention time or hydraulic retention time, let's say. So we have different ranges around 2 hours at average flow, and what is that, peak flow, and at design flow. But again, you don't need to mug these up. And where overflow rate, right, or overflow rate is something that we need to be looking at. So these are the primary design variables. And what else do I need to look at? As in, I need to look at whether I want to go for circular or rectangular, right? Why? We already discussed it. Easier to remove solids at the bottom, less maintenance cost, and more importantly, the construction costs are pretty less, the capital costs are pretty less. But rectangular, obviously more effective use of area, and here we see typically that the length to width, right, or length is typically more, let's say, right, because let's say, think of this, if you have this, assume that this area or top view, this is the top view, and this. So here you can have a lot of short circuiting occur, right. For example, you want the particle to settle down, right, but here you can have short circuiting occurring, as in not every particle that comes in at the influent, or you are not going to design it so well that you are going to have very good distribution and such, let's say, right. And obviously here energy dissipation, depending on the design, pretty good, and you have longer, what do we say, paths for the settling of the relevant particle, right. But here obviously people can use the side area more effectively. That's why people prefer rectangular to long narrow rectangles, or these kinds of rectangular sedimentation tanks to long narrow sedimentation tanks. But from the point of view of maintenance and cost, people go for circular sedimentation tanks, right. Inlet design, again a part of secondary design values. What are we concerned with? We, as I mentioned, we want to decrease the energy or dissipate the inlet energy, right, and you want to prevent cross circuiting, and you want to distribute the flow. And flow balancing among tanks, and also baffling, which is more or less a part of what we just discussed earlier, let's say. Weir design, right, again you want to have as quiescent flow conditions or laminar flow conditions as possible, and then you are going to have it. But we are not going to go into design here, but you can look at the relevant loadings here. So let's just look at one example out here. A primary sedimentation basin is designed to treat a wastewater that has an annual average flow. Q average is 300 meter cube per hour, and maximum 2-hour flow, Q peak. We looked at this 2-hour flow, meaning for let's say over this year, the maximum flow which was observed continuously over a 2-hour period was 550 meter cube per hour. Use these to determine the required diameter and depth, meaning a circular sedimentation basin. Assume that it is a conical bottom, so that no additional depth is required for sludge storage. As in typically, let's say, you are going to have some freeboard. We did not discuss this, or we did not mention this freeboard, because you are not going to plan it such that the water is up to the brim, and then you are going to have your effective zone and then your sludge zone, let's say, right. So you will have to take into account all these heights, but here we are only looking at this particular height out here. So how do we go about it? What do we have? We have the surface overflow rate, V naught, and we have the hydraulic retention time, theta is equal to volume by what is this? Q, V by Q, let's say, right. So how do we get this, or what does this tell me? This tells me the time that this particular water or the particle will spend in this reactor. Hydraulic retention time, for how long is the particle being retained in the relevant reactor. So again, it's pretty straightforward. Let's go through this. We have our surface overflow rate, but again there are two, what do we say, overflow rates given, right? So we'll have to look at it from both points of view. So we'll calculate the what do we say, case when we look at the average values. So 300 meter cube per hour average flow by what do we say, the relevant overflow rate at the average flow. So we get 200 meter square. Similarly for the peak, we will calculate that and we get 183 meter square. So, okay, so it seems fine in that context, but we will end up choosing the higher value, right? Because the one that we are going to choose needs to meet the design from both the average and peak what do we say, flows, and thus we are going to look at what is it now, the higher, or take the higher what do we say, area here, right? This is the plan area. That's something to note here, right? Always the plan area, at least with respect to the overflow rate. And then what next? Okay, we have the area, and then the diameter and depth. Well, that's again a pretty easy aspect. So we know that area is equal to pi d square by 4. So from that I can get the relevant diameter. Let's see, here we are done with diameter, and the next aspect is depth. So depth, obviously we have other values here, as in we have the hydraulic retention time. So this will give us an idea about how much time the water molecule will spend in the system. So theta equal to V by Q. So we have V equal to theta Q obviously, and average volume, or volume required based on average flow conditions. Let's say I get 450 meter cube. Based on peak flow conditions, I get 550 meter cube, right? So from that I am going to obviously choose the larger volume of the relevant tank, right? Because you can't have overflow, or you don't want to have overflow of your particular tank. So I choose the bigger, higher value, and I am trying to calculate the diameter. I have the volume, I have the area somewhere, right? I have the area, and now I can calculate the height, let's see. So I am now able to calculate both the what is it, diameter and the relevant height of my particular sedimentation tank, right? So that's a general aspect. It's just algebra out here. So let's just look at what do we say, typical values. Retention time, theta or TR. Some people look at TR, some people say TD, but theta is a better one because of obvious reasons. Okay, for water treatment, right, retention time is 2 to 4 hours, okay, and overflow rate is a typical overflow rate, right, is around this particular value. Again, overflow rate, we know that it's going to be equal to Q by cross sectional area. So that's why you have the units meter cube per day for the flow rate, volume of water per time, by the cross sectional area, not cross sectional area, I guess, pardon me, surface area, that's meter square. So that's what you see. And here in wastewater treatment, we have different, what do we say, sedimentation tanks. For grit chamber, when we are trying to remove only the bigger and inert particles, obviously retention time is less and surface overflow rate is higher, let's say, right. So obviously particles with what do we say, lower settling velocities will not be able to settle down to the bottom. Primary clarifiers, we increase the time, retention time, and look at the concurrent decrease in the overflow rate, let's say, right. And secondary clarifiers, which are going to come into the picture after the biological process, where we remove the organic content, and you have flock forming bacteria which settle down to the bottom, right. Obviously time is higher, again the particles are much lesser, and the overflow rate also is pretty less, right. So just an idea here, let's see. And let's just look at some pictures and wrap up this particular session. So here we have, long, what do we say, narrow rectangular basins, if I may say so, but okay, it's not that narrow, right. Ideally, let's say if I have something like this and each one was an individual, what do we say, tank, that would have been better. But here, as you can see, this is the inlet, two tanks in parallel, and then you have the effluent weir all out here, right, effluent all along here, right. But here they did not have just one chain, because as is mentioned out here, the sludge is pretty heavy. So they have only not only more chains, let's say, right, and drive gears and motors and such, let's say. Yes. So again, baffle walls, right? Again, not a great design here, right? Head end of sedimentation basin showing the baffle boards, and then you can see these what is that scrapes or such. You see the chain, so it's going to rotate in this direction, come down, right, and scrape it like this. Or depending on where they have their collection, it can be the other way too, right? So that's one aspect. Okay, so scraping sludge is going in this. This is the bottom one is going out there, and this one towards here. Let's say. So this obviously. Okay, so it was going in this direction. Let's see. It's going out like this, and then rotating up, and then again coming back. So that's what we see out here, right? So there are other kinds of what do we say settling basins, but where I guess the design is of crucial aspect. We know that you don't really require a lot of depth if you design it, let's say, right? But typically to provide for flock formation and more or less to have your what do we say sludge settle down well, you sometimes provide depth as high as 3 meters. But theoretically, if you look at sedimentation, you don't need to do that, let's see. So the way to do it as in provide more surface area, right? So more surface area and bring down the V naught is by providing these plate settlers or tube settlers. So this is one particular picture here, two plate settler modules, right, 1 and 2. So let's just see how it works. So water with flock enters here, and you have these plates, right? You have these plates out here, and you have this flock settling down here and then coming down. So this is counter current, and then the sludge leaves at the bottom, let's see, right? So these are all the settling plates. I believe we looked at picture earlier, and then the water comes out. The settled water or the water clear of the suspended particles will come out at this top, at this part, and I think okay. So when it's installed, this is how it will look like, right? Plate settlers from the top view, they are installed, and now you see that again details of the water discharge system from the plate settlers. It moves up from the plate settlers over the pipes and down through the control orifices, I guess. Okay, and here you see pretty clear water. Okay, so water comes in, comes up through the plates, goes through these particular circular orifices, and then is discharged into the launders, let's say, right? So that's one particular. You can see the clear what do we say water coming up from the tube settler out here. So tube plate settlers, you are more or less what do we say increasing the surface area and also making the process more efficient because you have compact systems now, right? And obviously wears, we will not go into that. Again, primary design variables, we looked at that, so I am going to skip this for now. Okay, so in India, again, people are still learning and we are still turning to what do we say improve ourselves. So this is the typical what do we say old fashioned weirs, not weirs, sedimentation tank and the weirs out here, weirs. Right, again not a great design looking at what we have, but I do not know the situation on the ground there, right. So that's what we have, and then water overflowing out here, right. So that's something to consider. And then what do we say sedimentation tanks, what is it that we are trying to do? We are primarily trying to remove the suspended particles, but along with suspended particles, some organic content which is suspended or adsorbed onto these suspended particles will also be removed. And again, will we have removal of all the suspended particles? Not really. So we have typically what do we say fraction being removed, let's say, right. And again, Indian aspects, the issue is that people don't maintain it and run the systems well. Design is always also not great, but again that's what we are trying to change by I guess learning here, right. So primary aspects or another aspect to consider is that BOD will also be removed, but you will typically not observe more than 35 BOD removal. And as mentioned earlier, we are primarily concerned with overflow rate and then the hydraulic retention time or the detention time and the height of the relevant sedimentation basin, let's say, right. And then hindered zone, let's wrap it up. Particles settle as a zone or blanket, right. That's something that we already look at. And one aspect here is that now the settling velocities are going to be relatively less. And again, water has to find its way out from under these or through these particles, through the interstices between the relevant particles, let's say, right. Because you have a zone, you are going to have a clear interface between the sludge and the above effluent. That's something to keep in mind. So hindered settling, we already looked at this, so I will move on from here. And compression settling, okay, we have a good picture out here. So here the water is squeezed out of the sludge, as I mentioned, right? It's not really particles settling down, but the weight of the particles above seeing to it that the water is squeezed out from the particles underneath, right? So that's why we call it as compression settling, let's say, right? So here we see, let's say first right now it's hindered settling, and then our zone, what do we say, settling, we see clear water, and then the hindered settling out here. But now already the sludge out here is experiencing compression settling and the transition zone in between, and then all the hindered settling is done. We just have the transition and the compression settling, let's say, right? And then we end up out here, let's say, right? So that's pretty much obvious, right? And again, as you can see, the weight and then all the water trapped out here is being compressed and released, let's say, right? So I'm almost done with my time, and we are also done with looking at primary sedimentation. So what next? I removed the suspended particles and some dissolved organic content and most of the suspended organic content. Next, I want to remove the soluble organic content, let's say, or the dissolved organic content, and that I am going to do by the aid of microbes, right? So with that, I will end my session and will continue this in the next session. Thank you.